So good morning. So is it visible? My screen?
Yes, sir.
Visible, sir.
Yes. Okay. So then we are going to start the common gate stage. This is the common gate stage. Okay. See, in the common gate stage, if you see, this is the gate which is common between the input and output side. You can take this input, you can apply here, and you can collect the output here. This is. So the common gate stage, this is the RD resistance, this is the M1 transistor, and RS is the source with source resistance. The source means voltage source whose internal impedance is RS. Okay. So now I am going to draw the equivalent circuit of this common gate stage, including the parasitic capacitances. So whatever the four capacitance we have discussing so far from this beginning of this frequency response chapter. So this is the source with source resistance. I think this is the current source which can be open, no problem. So this is the source. Okay, and this is the drain, and this is the gate. Yes. So this is the capacitor, one parasitic capacitor. Okay, this is one more parasitic capacitance. Okay, so I think there are many more capacitances. Okay, so they can be neglected with the they can be simplified with the what is that one, Miller theorem, like that. So finally we got, this is the simple circuit. Okay. Yeah. For finding the frequency response, what we should be do? The first requirement is transfer function of the circuit. Transfer function is nothing but it is the ratio of output to input. So then the transfer function should be rearranged in the form of poles and zeros. Then you can draw the pole or zero magnitude with respect to the frequency, or the entire transfer function response via frequency is called the frequency response. That is the procedure we are doing. Okay. Yes. So is the end out for the circuit? This is the common gate configuration, common gate stage, and whose small signal equivalent circuit, including the parasitic capacitance. This is this one. Okay. Where Vn is applied to the gate of the transistor, gate of the MOSFET. Okay. This is the CGS. CGS means gate to source plus source to body, gate to drain, and drain to body. These are the parasitic capacitances. Okay. Then see the parasitic capacitance, from the parasitic capacitance, from the small signal equivalent circuit, the input frequency or input pole is nothing but CGS plus CSB, get to source, source to body. Okay, so that means 1 by, this is all thing by 1 by what is that one? CGS plus CSB is the capacitance. Now resistance is required, is multiplied with the resistance is RS is parallel with 1 by, so GM plus GMB. This is the what? Omega input pole. Input pole is equal to 1 by, this is the capacitor, and this is the resistance. Capacitor and resistor. Okay. If you go back, gate to source and source to body, this is. And this is the one more resistance. This is the capacitor. This capacitor is multiplied with the resistance. What is the resistance? RS is parallel with the M1 resistance. This M1 resistance. M1 resistance is what? 1 by GM plus GMB. Understand? Hello?
Yes, sir.
Yeah. So this is the, so always you can find, I am talking about the input side. Input side means this is from this side. So from this side, you need to find the resistance as well as the capacitor, because omega is nothing but 1 by CRS, sorry. Okay, capacitor and resistor. So the capacitance value is it is pakka, and resistance value is this is the RS, and the M1 resistance is 1 by GM plus GMB. Yeah, here is that one. So that is the input frequency, input pole frequency. This is the input pole frequency. Pole frequency. Similarly, the output pole frequency. Output pole frequency means you should look into the output, find the R equivalent or output resistance, that is the RD only you got, and output capacitance is CDZ plus CDB. That means 1 by. That's it. So you can have one input pole and one output pole. Okay. Then, so the transfer function of this common gate configuration is transfer function. If you find the transfer function, and that means the ratio from output to the input, if you find the ratio, okay. So by KVL and KCL equations, then you will get this type of equation. V out by V in is equal to GM plus GMB into RD by 1 plus GM plus GMB into RS is multiplied by 1 by, this is one pole, this is one more pole. This is the input pole, this is the output pole. So this is the basic structure of common gate configuration transfer function. So here is, understand this one, input pole, output pole, and transfer function in terms of input and output poles. Understand?
Yes, sir.
Any doubt? Any Ramani garu? Any doubts?
Late sir, mention.
Okay. This is the basic structure. Okay. So here, so in this circuit, the capacitances contributed by M1 are connected from the input and output nodes to ground. Okay. At X is equal to, what is that one? CS is equal to, at X node is equal to, what is the capacitance? See, gate to source plus source to body. Okay. So already this is the our input pole, and this is the output pole we know. This is the, what is that one I told you? Basic structure of the transfer function. Okay. So that means you can see from one is X node, one is X node, and one more is at Y node. So Y node is nothing but this one, this node. And that means here. Okay. So yeah. So Y node, the overall transfer function is this is here. This is the one term. This is the another term. Two terms are there in the transfer function. What is the first term? First term is nothing but the low frequency gain. This is the low frequency gain. Gain of the circuit. Okay. So if we do not neglect R01, the input and output node interacts, making it difficult to calculate. Means in the previous circuit, in this circuit, for example, generally we will consider like this. The resistance we can take like this R0. We are not consider this R0. So since we are not considered this R0, that's why in the equivalent circuit, small signal equivalent circuit, we did not find anywhere R0 value. We did not find anywhere R. If it is there, then R0 will be coming here. R0. Okay. So this is the transfer function without R0. This is the transfer function without R0. Okay. So yeah. And now, so this is the yes. What is this? Yeah, I want to substitute omega. That means input pole and output pole. I want to substitute them in the transfer function equation. So then V0 by Vs is equal to, this is as usual, 1 by 1 plus s by what is that? Why s by omega in, and 1 plus s by omega 2, omega out, otherwise there. So now those values for this circuit, this is also common gate. Gate is common. So here is the one capacitor, here is the one more capacitor. This is the, you can say, CS, source capacitor and drain capacitors. Okay. So then the transfer function, this is the low frequency gain. Keep it as it is, 1 by 1 plus. So what is this one? Input frequency. That means input frequency means, so S by omega in. So in place of omega in, you will get what? So omega in. So CS by, that means S is multiplied with this one. In place of omega in, you will get CS by GM plus GMB plus RS, 1 by RS. Okay. Similarly, output. This is the output pole. That is 1 plus RD CD. So this is the two poles. The poles from this circuit, for this circuit. So this is the transfer function. Okay, this is the common gate. The earlier also common gate. But the thing is, here only we take the capacitor CS and CD, so that you must write the transfer function in terms of the CS and CD only. Okay. Hello? Got my point?
Yes, sir.
Yes,
Yeah.
sir.
So you know up to this one, this is what? This term is what? Low frequency gain. And this is, what is this format? 1 by 1 plus S by omega in is multiplied with 1 plus S by omega out. So for this circuit, omega in is, what is that one, omega in? So GM plus GMB plus 1 by RS by CS. And omega out is 1 plus RD into CD. Yeah, substitute these two omega values, frequency values, two pole frequencies in the equation, in the transfer function equation. Then you got this one. Okay. So here is my question is Z-in. Z-in means input impedance of the circuit. Input impedance means you can look into this side. This is the Z-in. What is a Z-in? What is the input input impedance of the circuit? Input impedance of the circuit is, you can write ZL by GM plus GMB into R0 plus 1 by GM plus GMB. This is already we know in the module 2. Module 2, common gate stays. You can go and verify this one. So then you will get the input frequency, input impedance is approximately equal to ZL by GM plus GMB into R0 plus 1 by GM plus GMB. Okay. The important property of this circuit is that it exhibits no Miller multiplication of capacitances, potentially achieving the wide band. So what is the uniqueness of this common gate configuration is? So in the common gate configuration, we are not applied any Miller theorem, and there is no Miller multiplication of capacitance. Miller multiplication capacitance means what? Suppose if you want Z1 is nothing but, so Z into 1 minus AV. This is the Miller multiplication, or 1 plus AV, that became based on the, what is that one? Amplifier gain. This is the what? The input impedance or input capacitance CI is equal to C into 1 plus AV. Input capacitance is equal to capacitance multiplied with this factor. That is called the Miller multiplication. So these two are not applied. The Miller multiplication is not applied. So that whenever the Miller multiplication is not applied, this is the circuit can be used for the wideband applications. Common gate can be used for the wideband applications. Got my point? Are you understand?
Yes, sir.
Yeah. So once again, I'm going to tell you, this is my common gate stays. This is a simple common gate circuit, and this is the common gate with parasitic capacitances. Okay. Then from the common gate, from the common gate, simple small signal gain or small signal circuit, see the input and output poles are written like this. Then the overall transfer function structure is this one. Okay, so now I want to so what is the first term? The first term is this much is low frequency gain, and this is the two poles. Then take this circuit for this common gate circuit. So this is one capacitor, this is one more capacitor. Okay, so for this capacitors, I can write the transfer function. The transfer function I can take from the previous circuit, common gate circuit. So here the omega in and omega out both are different for this circuit. Omega in is nothing but, so input capacitance is multiplied with the input impedance. Input impedance is Zeta, you can say. Is multiplied with the CS. Okay, what is Zeta? Zeta is here 1 by GM plus GMB plus 1 by RS. That is a Zeta. So similarly, output resistance is RD and output capacitance is CD. So that is, you can get the 1 plus CD into RD CS. This is. So here is the input capacity, input impedance value I have taken. Sir, good morning, sir. Is approximately equal to ZL by GM plus GMB into R0 plus 1 by GM plus GMB. Got my point up to here? Hello?
Yes, sir.
Yes. So then the uniqueness of this common gate configuration is, common gate stage is, we are not applied any Miller theorem and there is no Miller multiplication of the capacitance, so that it can be used for the wide range of applications. Got my point? Yes. So note, however, that the low input impedance may load the preceding stage. This is the one of the drawback. What is the drawback? Low input impedance. What is the Zeta formula? This is the Zeta formula. Since this is high and this is high, of course, it may be low. 1 by higher value is nothing but low value. Okay, so then that is one of the drawback. So that because whenever it is having a low input impedance, it may be the previous stage, it becomes the loading effect. It may be having the loading effect on the previous stage. So, and one more, since the voltage drop across RD is typically maximized, RD, to obtain the reasonable gain, the DC level of the input signal must be quite low. So DC is also low. Two things. One is the what it may provide provide a loading effect on the previous stage, and moreover, so across the RD there may be a more maximum voltage will be dropped, so that what is that one? DC level, DC voltage of the signal may be quite low. For the reasons, the CZ stage finds two principal applications. One is the amplifier in case as an amplifier in cases where low input impedance is required, and one more is cascade stages. So in the cascade, we have a common source and common gate structures is nothing but the cascade stage. You can apply, you can use this CZ in the, what is that one? Cascade stages. And one more application of the common gate is, what is that one? So where the amplifiers where the input impedance is low is required. Okay. Hello?
Yes, sir.
Yeah. So two applications. One is low impedance amplifiers, and moreover cascade stages. Okay. Suppose if CLM is not negligible, channel length modulation is not negligible, what happened? So the input impedance of the CZ topology depends on the drain load if lambda is not equal to 0. So the earlier, whatever the earlier analysis we have done for the common gate configuration is just we assumed what channel length modulation is 0. If the channel length modulation is not 0, the input impedance of the common gate topology depends on the drain load. Okay, suppose this is already, this is what input impedance of the M1 when we are seeing into the source, from the source. What is the ZL? Here ZL is nothing but load impedance is nothing but RD is multiplied with 1 by CDS. This is the what ZL value. Since Zin now depends on ZL, okay, so here from this one, this is the input impedance, this is the ZL. Now your input impedance depends on the output load or load impedance. Okay, it is difficult to associate a pole with the input node. Okay, it is difficult to associate a pole with the input node. So whenever the dependency is there, we cannot directly calculate the input pole. So before that, we calculate the input pole Wi. W in is equal to 1 by GM plus GMB into 1 by RS. Okay, is multiplied with 1 by CS. This is the input pole for the previous circuit. So we directly calculate this one because this is the R equivalent and this is the C value. So omega in is nothing but 1 by RC, 1 by RC. But whenever the input impedance depends on the load impedance, we cannot directly connect the calculate the pole of the input pole. Got my point? Are you understand?
Yes, sir.
Yes.
Yes, sir.
Yeah. Now, one question is, calculate the transfer function of and input impedance Zin of this circuit. For this circuit, find the transfer function and input impedance. Okay, see what is the difference between this and the first picture in today's class? This is R0. I told you there R0, we are we neglected the R0. I think we are not considering the R0 value. Okay, but now if you take the R0 value, what is the transfer function? Okay, now we'll do one thing. For this common gate structure, this is a common gate structure, no doubt at all. For this common gate stage, draw the small signal equivalent circuit. See, this part is here. Yes, this part is here. And for this, we need to draw the what? Small signal model. This is the small signal model for that part. And this is the load capacitor. Yes, load capacitor. And this capacitor current source is open. Got my point? While you are drawing this small signal model, then independent source, I think current source is open. Okay. Understand how to draw the small signal model for this common gate configuration?
Yes, sir.
Yes. If it is okay, then I will move. So we need to find the transfer function of this fellow. Okay. So first of all, find the current to the RS. What is the current to the RS? How much current is going through this one? How much current is going through this one? Okay, that is the current to the RS. Okay, see, to find the current to the RS, IRS I wrote is equal to minus V out is multiplied with the CL S plus V1 CNS. How means? Yeah, see, the current through this one is nothing but, this is ground, and this is ground, and this is ground. You can take this all these three. Then the voltage drop across this fellow is nothing but what? So V, not voltage drop, current. Current is what? V out by 1 by impedance. Impedance is what? 1 by CLS. That is equal to, so V out is multiplied with CLS. Okay, that is one factor. So this is the minus you will get because of this direction. And now, what is this one? because of these two are parallel. I think this is ground, this both are the same node, and another node is grounded. You can take like this, you can write like this also, no problem. V1 plus minus. Now the current going this side is, you can say, so V1 by impedance 1 by C in S, that is equal to V1 C in S. This is one current, this is one more current. Okay, so that the current going through RS is nothing but simply, what is that one? IRS is equal to, so minus V out into CL S plus V1 into C in S. This is the current to the RS. Are you understand this one?
Yes,
Hello? Ramakrishna Radhainda?
Yes, sir.
Okay. Sushma Radhainda? Sushma. Tarun, are you understand?
Yes, sir.
Yeah. So very simple. Definitely you will have some doubt how to write this one. Because of this one, you can draw like this. This one. Yeah, plus is this side. Okay. Ground. This is plus, this is minus V1. And you can write this node also. Yeah. You can join this and this. Then this is V out ground. Then this current is nothing but this current plus this current. This current, sorry. So that is the, I wrote, that is only the I wrote like that. Yeah. So that here is my equation is right for this one. So IRS is equal to minus V out CLS plus V1 CNS. Okay. Now, so I want to write the KVL equation for the input loop. What is the KVL equation for the input loop? Yes, for the input loop, KVL equation is, if you go back, yeah, this is the input loop, means this is the input loop. This is my input loop. If you write the KVL equation, so minus to plus plus or plus to minus minus V1. Okay. So, and plus across this drop, RS is equal to, RS is multiplied with current. This is the IRS. Plus to minus, then becomes plus V in. This is the equation. This equation. Okay, understand how, what is the loop? The loop, you can understand, the loop is like this. The loop is, this is your loop to write the equation. This is the loop. Understand? So plus to minus, earlier the current direction is this one, plus minus. Earlier current direction is this one. Okay. So that you can write, or you can say this is the plus minus, okay, or minus to plus, you can take, this is the minus V1 is equal to, RS is multiplied by current IRS plus V in. This is the equation. In this equation, I want IRS. Already I wrote IRS. The IRS value is this much. Okay. So IRS value is this much. Got my point? Hello?
Yes, sir.
Yeah. Now substitute the IRS value here. Then what is that one? Minus V1 is equal to V in plus RS is multiplied with, this is the IRS value is how much? Minus V out into CLS plus V in CNS. From this equation, separate the V in terms and other terms. From that, after separation, find the V1 value. The V1 value, V1 is here and V1 is here. So that if you bring this V1 in this side, this becomes 1 plus C in S into RS. Okay. And the numerator V in and V out is there. So that finally your V1 is equal to V in minus V out into CLS into RS by 1 plus C in S into RS. Understand?
Yes, sir.
Yes, sir.
Yes. Okay.
Yes, sir.
Yeah. So from the KVL equation, first you first find the current to the RS value. Then from the KVL equation, you have an equation V1 is equal to RS into IRS plus V in, and substitute this IRS value here. Then rearrange the equation for getting the V1 value. Then V1 value is V in minus V out CLS into RS. So by 1 plus C in S into RS you got. Okay. So after getting this V1 value, then write the equation for the output. What is the output equation? Again, go to this one. What is the output equation? Output equation V out is nothing but, this is V out is nothing but, V out is equal to, okay. So see, this is the ground and this is also ground. You can write one thing. So R naught is multiplied. This is the R naught. This is the R naught. Okay, R naught is multiplied with two things. This side and this side. This current is how much? Suppose current is coming like this. This is the this current. This is nothing but V out. So V out. If this voltage is V out, the current is this side is V out by sorry, R naught by what is that one? No. R naught current current and yeah, this one first take this one. Yeah, this current plus this current plus this current. You can write this current is sorry. So V out by 1 by CLS plus this current is V out by R naught plus this current is GM into V1. Okay. So again, from this you can write separate the terms. V out is equal to, then V out is equal to, you will get R naught is multiplied with minus V out into CLS minus GM into V1 minus V1 including this term. Okay, so now you need to substitute this V1 value earlier, whatever the V1 value calculated here. So substitute this V1 value here and here. So then you will get the output equation in terms of input and output. Then separate the V in terms and V out terms. Then take the ratio of these two. Then you will get the transfer function. Yeah, this is the transfer function you got finally. So after writing the V out equation, substitute the V1 value in the V out, this value. Then your transfer function is getting like this: 1 plus GM into R naught by R naught CL C in RS S square plus R naught CL plus C in RS plus 1 by GM R naught CL CS into S plus 1. This is the S square term. Sorry, S square coefficient. This is 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 the S coefficient. Yes. Okay. So this is the transfer function of the circuit. Okay. So now here, what is the Z in? So body effect cannot be included by simply replacing body effect can be included by simply replacing GM with GM plus GMB. So wherever GM is there, that must be replaced with the GM plus GMB. Then we can include the body effect also. As expected, the gain at low frequency is equal to 1 plus GMR naught. For Z in input impedance, replacing ZL with 1 by CLS. Then this is already, you know, our Z in equation is input impedance is what? 1 by, what is that one? You got 1 by yeah, ZL, sorry, ZL by GM plus GMB into R naught plus 1 by GM plus GMB. This is the equation. Earlier, already we know Z in equation for the common gate configuration. So where we say that means I told you this ZL value. Okay, what is the ZL value here? Here ZL value is nothing but 1 by CLS. Okay, then substitute this 1 by CLS. Then in this equation, then what happened? This term, here is the term. Sorry, here is, sorry, here is the term. Yeah, here is the term. So, and second term is this much. So 1 by Zm plus Gm into R naught. Yes, this is into 1 by ZL. What is ZL? 1 by CLS. So this is. So note that CL or S increases, Zn approaches to 1 by Gm plus Gmb. Suppose either CL increases or S increases. What happened? This becomes 0. 1 by higher value is equal to very, very small value. Then Zn is equal to only this one. The input pole can be defined as, now the input pole is nothing but 1 by, what is Zn value? Zn value is nothing but, so Rs is parallel with this one into Cn input capacitance. Okay, understand this one?
Yes, sir.
Any doubt? Any doubt?
No, sir.
No doubt, sir.
Okay. So this is the input pole frequency is equal to 1 by RC, 1 by RC. This is the R value, this is the C value. Here R value, RS is already there, source resistance is parallel with input impedance. This is the input impedance. So this is the input impedance because this part is negligible with this case. So that only Zn is simply 1 by Gm plus Gmb. Yes. So in this problem, he asked to calculate the transfaction and input impedance. Transfaction already calculated. Input impedance also we calculated. Now he is asking explain why Zn becomes independent of CL as this capacitance increases. So Zn value is already this is. Zn value is already this is. In this already CL is there. But when CL increases or frequency increases, what happened? CL increase means frequency increases. What happened? This part becomes 0. 0 multiplied with anything is 0. Then this is only the thing. He's asking why ZL is independent of CL at high frequencies. The reason is this is because CL lowers the voltage gain of the circuit. The whatever the CL value you have, that will lower it will make them reduce the gain of the voltage, thereby suppressing the effect of the negative resistance introduced by the Miller effect theory through R naught. So negative resistance, already we discussed about this negative resistance. So I can show you back, I can go back to show you. Negative resistance means negative resistance means yes. Suppose if you take this one, R out, for example, R out is equal to, if you write R naught by 1 minus AV. In this equation, suppose AV, this value is greater than 1. What happened? This value becomes negative. So then I can say R out is equal to minus R naught, minus R. This is the negative resistance. This is called the negative resistance. so that negative resistance introduced by the Miller effect true or not in the limit CL shorts the output node to ground and R naught affects the input impedance negligible. So whenever CL value is increases, that means high frequency, what happened? So generally the CL, what is the role of CL? It reduces the gain of the old circuit. So thereby what happened? The effect of the negative resistance introduced by the Miller effect, because if A is greater than 1, then the resistance becomes negative, which was produced by the Miller effect, because once the Miller theorem is applied, then only you will get the Z1 is equal to Z by 1 minus AV, 1 minus AV. Okay, so the negative resistance is introduced by only Miller effect. So, and in the limit, CL short the output node to ground. So whatever the CL is there, then becomes short circuited. So that's why short circuit to ground, then R naught becomes the negligible. Okay, so whenever this is short circuited to ground, short circuited like this, then R naught effect is negligible. Okay, then what happened? Your Zin is independent of load values, output values. Okay. And one more thing is, what is that one? This is also CZ, common gate configuration. Common gate configuration. Yeah, please bear with me a few minutes. So assume all the above analysis, whatever the analysis we have done. Okay, everything with zero gate resistance, gate input resistance, zero input with the gate series. So this is the another assumption. See, earlier this is like this. There is no RG value is equal to 0. So earlier, whatever the common gate configuration we have discussed so far, everything is zero impedance in series with the gate. But in practice, so because of biasing circuits are there, so there is a finite amount of the resistance which is connected in series with the gate. Okay, like this. So when we include this, when we include all the capacitors, transfer function is the third order. So understand my argument? Hello?
Yes, sir.
Yes, sir.
So my argument is earlier this RG value is how much? 0, which means we are not taking any gate resistance in series with the gate. But now what I am telling you, because biasing circuits already connected to the circuit, biasing is required. So we need to connect them. So because of those biasing circuits, some finite amount of the resistance becomes in series with the gate. So that I am going to adding here. And one more thing, already I am telling you number of times, there are 4 capacitors or 3 capacitors are there, parasitic capacitors. Okay, but previously we used 2 things. One is CZ, one more is CS. Sorry, CD and CS. CD and CS. Okay, when you use the 2 things, 2 capacitors, then you got the second order equation. If you include 3 capacitors, then you will get the third order equation, transfer function. Am I correct?
Yes, sir.
Yeah, each capacitor will introduce one pole, let's assume, or one order, because 1 by CS. Okay, so 3 capacitors means third order, 2 capacitors means second order. Okay. Yes. So anyhow, when we include all the capacitors, transfer function become third order. But what happened? I used here is CGS, gate to source, and similarly we need to use the drain to source, and what is that one? Gate to drain also. But for the simplicity, for simplification purpose, I used only one thing, that is the CGS, gate to source only I used. So that now the equivalent circuit, small signal equivalent circuit of this fellow is, yeah, this is this one, no problem. And this is the load, and the rest of thing is here. This is. Okay, got my point? This is the RG is here. Got my point?
Yes, sir.
Yes, this is the small signal model equivalent circuit for this circuit. Whatever the common gate configuration with finite amount of gate resistance in series with the gate. So this is the, okay, here I'm going to tell you one thing. I'm considering only CGS. Okay, that's why my transformation becomes somewhat easier. So here, so this current, because of this open circuit, okay, this current is equal to this current. Okay, clear? So that means I can say GM V1 value, that is current, is equal to how much? This current. What is this current? V out by RD. Of course, minus, plus to minus, minus V out by RD is the current. Okay. So from this one, what is the V out? V1, sorry, V1 is equal to minus V out by GM into RD. GM into RD. Got it? Got it or not? Yes. Now I want to find the current to the RS. What is the current to the RS? Okay, because this is the ground, you can connect like this. Take the simple loop equation, then you can find the current. Because this is also open. Okay, so you can take the simple one. Then IRS current to the RS is equal to. So this is the V1. The voltage at this point is V1. Okay, so and V1 is multiplied with GM plus CGS into S. This is okay. This is the, what is that one? Otherwise, you can say this same current is coming like this. So that GM plus V1. What is this capacitor? Impedance. Impedance is 1 by CGS. That is impedance. That's a V1 into GM. This component, and this component is V1 into V1 by 1 by CGS. That's this one. So now V1 value, no, this is the V1 value. You can substitute. So IRS is equal to, so minus what is that one? GM plus CGS into S. Okay, V out by GM into RD. Got my point? This is the, I substituted this V1 value in here. Then I got this equation for the current to the RS value. Then I want to find the current to the RG. So current to the RG is equal to IRG is equal to, what is that one? V1. This is the V1 into this impedance. V1 by this impedance. Sorry. What is this impedance? 1 by CGSS. So that it becomes V1 into CGSS. Okay, that is equal to V1 again, you know, here same thing. So that you can get the minus CGS into S into V out by GM into RB. So that is the current to the RG. So now write the KVL equation. So KVL for this loop, first in inner loop. So write the KVL equation for this loop. Then you will get this one. So V in, yeah, minus plus V in. So minus RS is multiplied with the current, this current. RS into IRS. Okay, and plus the drop across this fellow. Plus minus. Okay. So what is this one? This is the V1 you can write. V1 you can write. This the voltage across this fellow is only V1, so that you can write minus plus plus V1. And this is the drop across RG. Drop across RG. This is the plus minus because of direction. So minus RG into IRG is equal to 0. This is the KVL equation. In this, V in minus RS value, no, IRS value, substitute this value. Okay, plus V1. So what is the V1 value? This one value. This is the V1 value, substitute here. Minus RG is multiplied with IRG. This is the IRG value, substitute here. Then your equation in terms of input and output. Then take the ratio of those things. Then you will get V out by V in is equal to, so GM RD by, so RG plus RS into CGS into S plus 1 plus GM into RS. This is the transfer function you got. Okay. So from this, how many capacitors there in the circuit? Students, how many capacitors there? Hello?
3.
Only one capacitor, sir. How you get the 3? Only one, I told you beginning. So I'm considering only one. That is the CGS.
CGS.
So that only one root will come, one pole will come. Okay. That means one first order, order 1 will come in the transfer function. Only S term is there. So from this, what is the pole? The pole is equal to, pole is equal to, if you want to take the S common, then it becomes what? 1 plus GM RS by this thing. So 1 plus GM into RS by RG plus RS is multiplied with the CGS. That is the pole. Okay. Understand this one? Pole. If you see the denominator, you should write S plus something. S plus something. Okay. S plus something means, so what is the S coefficient? It must be divided with this entire denominator. Then you will get 1 plus GM by RS by RG plus RS into CGS. Into S. Okay. CGS only, not S. CGS. Okay. If RS value is far greater, okay, then the output of the circuit drops at high frequency. Whenever RS value is far high, okay, the output impedance of the circuit drops at the high frequency. Understand? Hello? Yeah, this is the derivation for this circuit. Only I have considered only one capacitor. You can consider one more capacitor, then you will get the second order equation transfer function. If you consider third capacitor, then you will get the third order capacitor transfer function. Okay.
Yes, sir.
If it is okay, then I will stop the class. If you have any doubts, I will clear the doubts first, then I will stop the class. Hello?
Sir, this derivation and the text form,
Get it Japan.
derivation in the text form, sir, text form, or the video lecture.
ఇక్కడ రాసింది దిందేనా
Okay, sir.
నేను రాసేస్తాను రాసింది డెరివేషన్
Okay, sir.
ఓకేనా
Okay, sir.
ఎస్ యా if no doubts I will stop the class.